Hello, everybody. I'm Dan McKeaton, working with my father, Glenn Smeaton, here on a presentation about using diagnostic lab analysis to assist in wastewater plant operations. Glenn will be leading you off with a bit of an introduction to how this applies to operators and understanding when and how to start taking advantage of lab services in order to assist your plant operation. So I will hand the mic over to him.
Hello. I've worked with operators for over 40 years, and I've always been amazed at all the things they keep track of in the course of their work. And we're talking today about problem solving. And I remember from my high school and college professors telling me you have to change one variable at a time if you're using a scientific method. But operators have all kinds of variables. I'm reminded of the movie I saw, Support Your Local Sheriff, with James Garner. And he was looking at the badges he was going to use, and he picked up one that had a bullet in it, a bullet dent in it. And he said, "This must have saved the man's life." And the mayor says, "It would have if it hadn't been for all them other bullets flying around at the same time." And that's the way it is with operators. They have to deal with multiple variables, and sometimes it's very difficult troubleshooting. But they do the best they can. And when they can't, they have to get help from outside help. Where do you get it from? Well, they can go to a commercial lab, or they can go to design engineers or operational consultants. We're talking today specifically about getting the most from working with a commercial lab. Now, they have all kinds of equipment and they're willing to work with you and everything else. But first, you have to make sure that you're giving them quantitative and qualitative information as to what you need to solve the problem. You have to make sure that you have quite right time of equipment and capabilities to do the solving of that problem. And you need to select a vendor that's working with you and will help you clearly identify your goals. Now, one of the important things about it, after you have a clearly measurable problem to solve and a plan to solve that problem, and you start to taking your samples, it's very important that you have a specific sampling procedure that you and the lab that you're working with understands clearly what has to be done. For instance, if they have a grab sample requirement and you take a composite sample, you'll be getting a much lower variable, or you won't be able to find a specific problem. Or the other way around, if they want to know about a longer period of time, you'll need a composite sample, and they have to come from the right locations. So you can have everything done right in the lab, but mess up a sample and the sampling, and you won't be able to get the right results. One situation I worked with years ago, there's an operator was taking a sample to the lab, and they had a lab on site, and he was picking up the sample on the far end of the lab and walking to the lab with an open pail of the sample in it, sloshing the water out as he walked to the lab. And what he was sloshing out was the clear water from the solid settling. So when the lab ran the test, it always showed that they had too high level of solids in their aeration tank because the operator concentrated it for him before he got to the sample. They kept wasting their sample and wasting their sample, or wasting their plants activated sludge, until all of a sudden they almost totally wiped out all their solids before they figured out what was going on. So they had to solve that sampling problem. And the people in the lab had no way of knowing that was going on. And so in getting the most from your lab, that's the most important thing for quality. Samples have to be located where you take them. You have to know how they should be collected. You have to know how they should be stabilized, if they should be stabilized, and how quickly they have to get to the lab in order to get good results. And then the lab will take from there and do the testing, getting results. And the final thing you have to do there is to make sure, if you get directions from your consultants or your lab, that you follow those directions specifically. So why can't you run your own testing? And many plants have a fairly sophisticated lab, the larger plants especially, and have people that can do good lab testing. But they can't afford equipment for an occasional test, that some very specific types of equipment and capabilities to do the test. And they don't have the time for it. And here's the important point here now, and you have about roughly 5 responsibilities in coming to work and solving a lab problem. The first, as you walk into that plant, is safety, personal safety. You should be able to walk into that plant healthy and walk out of that plant healthy every day you work there. That's number one. Number two is public safety. You don't want kids breaking into your lift stations or animals getting into your plant, pets jumping in the tank. All these things have happened over the years. And fourth, or third is planned maintenance. You want to make sure all your machinery is greased and running properly and maintained properly, because if it breaks down, it isn't going to work for you at all. Finally, plant operations, like the driving of the car. You have your car well maintained, then you get in and drive the car. And all that is important. But if you cut into those first 4 steps for the 5th one, which is testing and solving problems, your lab test can be the most expensive decision you ever made. And you might not even get good results, besides for not having the right equipment to work with. So that's the most important thing to remember with from the operator's point of view. Working with a lab, you have to know what to do and how to do it and who gets the sample and how fast they should get that sample. Now I'm going to turn it over to Dan, and he'll talk to you more about from the lab point of view.
All right, hello again. So I'm going to lead off with just a couple of definitions here. Usually we refer to diagnostic and routine testing. This presentation will of course be focused on diagnostic lab analysis, but there's a couple distinguishers between these two types of testings. But the primary things are diagnostic lab tests tend to be more specialized and intended to address a specific concern, whereas routine you are required to run for the operation of your plant, such as looking at effluent values. But the main problem with diagnostic lab analysis is it tends to be more expensive than the routine analysis, so people like to run it less frequently, even if it would be more beneficial if it were integrated into the plant routine. So lab testing can provide a better understanding of your system, but you need to remember that a lab test is only one point in time. So you shouldn't be using a single lab test to be able to analyze the health on your plant. You should look at a number of lab tests and be able to compare unhealthy times to healthy times in your plant operation to have a good sense for what's going on. So I'll start off with a bit about routine lab testing. Routine lab testing is, of course, vital for proper plant operation and function. You need to make sure that your plant is doing what it's supposed to do, which of course is letting the bacteria in your system remove all the nutrients in your waste stream to produce a clean effluent. Larger plants tend to perform a lot more on-site testing. A lot of smaller plants may send out a lot of their routine testing because they lack staffing as equipment, as was previously mentioned. But the other things are many plants will do routine settling tests on site. This is very important to understand how your sludge is behaving, because good settling is the key to good operation in activated sludge systems. And sending out routine analysis to your commercial lab in a lot of these smaller plants cases can help save time, produce better results, and provide valuable information to help with plant operation. Diagnostic lab analysis is intended to help determine the cause of a problem occurring in a wastewater system. For example, if your plant is having an issue, say you have an activated sludge plant, it's starting to produce a lot of foam, you want to know what composition or what's making up the foam, and you can't always tell that on site, so you send it to a diagnostic lab site who might be performing something like microanalysis. They can look at it, they can tell you if it's a filamentous foam or if it's not a filamentous foam, and then they can help you move forward from there. Diagnostic lab analysis takes a deep look into plant function, and it's a lot more complex than routine testing and targeted towards a system. With that in mind, diagnostic tests are very important to run when your plant is running normally, so you can contrast that with when your plant is not running normally. And that's just, it's nice to have a mapping. Whenever your plant is operating well, you might want to send out some samples for diagnostic lab analysis to a couple of sites. And it's nice to do this at different times of year as well. So say your plant is operating well in the fall, it might look quite a bit different microscopically and have a lot of different characteristics than when it's functioning well in the summer, because the bacterial population and characteristics of your plant are always evolving at all points in time. So if you want to understand how to compare healthy function to unhealthy function, you need to know how your plant would operate at what time of year in what environmental conditions, in what loading conditions, and compare it to your plant when it is upset. So types of diagnostic lab analysis. I have a big attachment to microanalysis, as I'm sure you'll notice in this presentation. But this is looking at a sample with a microscope for definitive characteristics to identify the cause in a problem. Chemical analysis is usually run by many of the commercial labs who also run things like your standard effluent data, but you can look at things like nutrient balance in your sample, maybe if toxins are entering your system, that kind of thing. And you can look at loading changes in terms of the waste composition and be able to identify if any changes are causing a problem. And treatability studies are kind of like the last resort option if you're not able to solve the problem with other ways, because they tend to be fairly intensive in terms of the work put in. They tend to be expensive. You're kind of trying to replicate a plant, and you can start altering a bunch of different variables at the same time side by side, so you can eliminate different possible problems more quickly and determine an effective solution. Whereas in a if you were trying to just make changes on site, you'd have to wait about 2 weeks between each change at least. A couple sludge ages is ideal in activated sludge systems to determine if your change is doing what it's supposed to do. So a couple other things we have here broken under. So chemical analysis, we have ATP analysis and DNA sequencing I like to talk about a little bit, and then we have treatability studies. So we're going to be talking about how and when to apply diagnostic lab testing for your lab, what uses do different types of diagnostic tests serve, how to determine what sort of diagnostic test to perform, and how to use information provided to improve plant function. So when do you run a diagnostic test? You run diagnostic testing when your plant is not functioning properly, but you also want to run it when it is functioning properly. This all has to be within reason of the expenses your plant is able to deal with. So ultimately, the more frequently you run diagnostic testing, the better. But there are limitations in what you're able to run. Microanalysis is typically $300 to $400. That's not always a big deal to run frequently, but sometimes it is for some smaller facilities. But you need to kind of weigh how frequently to run the test so that it's beneficial to your system without doing excessive testing and wasting money. So how do you do it? First, you have to precisely identify what the problem is so you can describe it to someone else. What were the symptoms you're observing on site? Foaming, bulking? Are you not getting good enough BOD removal? Are you having issues with high effluent ammonia? There's a bunch of different options that could potentially be the problem. And you also want to look at your system the last few weeks and see, is anything changing? Could a change have made a difference in how my plant is operating? For example, if you're sitting there in the end of October, the outside temperature in Wisconsin, I work out of Wisconsin, so we have a lot of issues with this, may drop from being about 60 to 70 degrees Fahrenheit all the way down to 30 degrees very quickly. And that can dramatically affect the temperature of the waste stream entering a system. This might really mess up a bacterial population because they need time to acclimate to that sort of changes. So you might lose nitrification and see high ammonia leaving your plant. So then you also have to figure out what type of lab do you need to work with. And ultimately, you're going to have to start contacting labs. You might want to start with the lab you're used to working with And if they don't run the type of testing, they should be able to help you point you in the direction of a lab that does run the testing you're working with. But is this problem something that could be diagnosed microscopically, chemically? A lot of plants will start with doing some additional chemical analysis if they notice a problem because they can work with the same lab. But that typical routine lab doing the chemical analysis doesn't necessarily have the equipment and experience to do a good job with microanalysis. So you might move on to microanalysis afterwards, but you kind of have to think about your problem and do different analysis depending on what it is. And it's also good to look at historically how you've solved the problem in the past in order to figure out what type of diagnostics might be beneficial. So I'm going to lead off with a bit about microscopic observation, which I am the most experienced with this type of lab work. And it can be a useful diagnostic tool for many reasons. But microscopic organisms grow and change very rapidly, and they're very sensitive to changes in plant conditions, be those environmental or loading conditions. So you'll be able to see different populations appear depending on how the conditions of the plant is. You might have low dissolved oxygen indicator organisms showing up if you're having a problem with your aeration system. You might have nitrogen deficient stuff starting to show up if you have um, something like a grape juice plant discharging a lot of waste, which is very high in sugar and low in nitrogen. That can throw off your nutrient balance, which would mess with your microscopic observations. Another nice thing is if you have somebody who's experienced performing microscopic observations, you can get a really quick turnaround time and have results quick enough that you can start to address them on site as efficiently as possible. So a couple things they look at with microanalysis. One would be flock structure and sludge age. So you can look at the flock structure and tell a lot about how a plant will be functioning and a lot about what sort of problems are occurring on site. So on the left here, I have a nice big flock, which looks pretty well condensed. It's irregular in shape. There's a little bit of filaments here at the top of the flock, but overall, if you were to see this flock in a microanalysis sample, this would be encouraging and you'd be assuming the plant would have good settling conditions. Whereas over here, you might see these pin flock, and some of these would settle very rapidly. They're very small and rounded, but a lot of them will not settle properly. You might have a lot of suspended or free bacteria in solution, like you can see a bunch of these little specks here are free bacteria. So you can look at these kind of things, and once you start seeing the form of the flock, you can get an idea of what sort of operational changes might be needed in order to correct the issue. Now, typically when we see pin flock, you might assume your sludge age might be getting a little high, you might have a toxicity issue occurring, or you might actually be over aerating and breaking up your flock, something we've seen a number of times. So another thing you could look for is filaments. Now you'll see a lot of filamentous analysis being applicable to foaming and bulking problems in a site. So here's just a couple common filaments. We have Microthrix parvicella on the right and Nocardioforms on the left. Both of these filaments like fat soils and greases. So if you were to see either of these growing in mass, you might have an indication that you have a lot of fat entering your system, and you may want to take steps to address that problem, or at least pinpoint the source of the fat entering your system. So another thing you could be looking into is bulking due to filamentous organisms. So here we have a couple filaments. This is type 00410675 in the top left. This is type 1851 in the top right. Bottom left, you're looking at O21N, type 021N, and then on the bottom right, you're looking at S. natans. So these four filaments all indicate different things, but they can produce similar symptoms, which is that your sludge is bulking, which means it'll take up a large volume of space. You won't have you'll have a thicker sludge blanket in your clarifier, regardless of how much active bacteria you have. And it can be difficult to operate your plant because you don't have enough clear water to maintain good settling in the clarifier. So you could look at all of these filaments and assess what conditions they usually appear. For example, type 021N is usually associated with nitrogen deficiency, or it could be associated with bleach. We actually have an interesting plant we worked with, which had a ton of type 021N growing in their system, and it was because they were trying to chlorinate for filaments. this filament happened to be resistant to chlorination. So when they were bleaching, they were actually killing a lot of their healthy bacteria and leaving the type 0 to an N. So they had these huge tangled balls of type 0 to an N making up the majority of their sludge volume. And it was really a mess, and it took quite a while to address the problem. They had to supplement nitrogen for an extended period of time, and that sort of thing is another thing a microanalysis lab could tell you. If a filament might not respond well to chlorination, chlorination is kind of a standard treatment for filaments, so they might be able to give you some insight into why you would or wouldn't undertake some sort of plant treatment. So another thing, people love to look at higher life forms in their wastewater plants, probably because they're easier to see and they do the most interesting things when you look at them under the microscope. This is what we have operators doing microanalysis. A lot of the time they'll talk a lot about these, and they are kind of fun. On the right here, I have this phase contrast image of an amoeba. You can see them slowly creeping around with their pseudopodia, and they're going to be a good indicator that you have a lot of free particulates in solution because they like to engulf single bacterial cells and kind of slowly move around. So when you have a lot of free bacteria, amoebas tend to be prevalent. Stalked ciliates on the left here are a good indicator organism. They have like a vacuum cleaner head which begins to suck bacteria into their stomach, and they help produce a nice, well, they don't really have a stomach, but they're stomach-like organelles. They typically are like a final polish to get to remove free bacteria from the system. So your plant is already starting to look good. Then these help polish it up to produce a really clear effluent. So plants with healthy stalked ciliate populations tend to produce very clear effluents. So here we have our even bigger fun organisms, the metazoa. These are just a few we commonly see. This is a gastrotrick. It's kind of interesting. They swim really fast. You have rotifers. Everybody likes their rotifers. You have your nematodes, which are up here on the top left, and then our bristleworms in the bottom left. And these aren't always the best indicators. Typically, if you're seeing bristleworms, you know your sludge age is way too old. You shouldn't really see any of them. Rotifers are kind of good to see one or two, and nematodes are okay. They're kind of like similar conditions to rotifers, but they tend to be a little bit more or less nematodes tend to be a little more resilient to adverse conditions like low dissolved oxygen or mild toxicity than rotifers. So the rotifers are kind of your good higher life form. You kind of want to see one or two because then you can be confident that toxicity has not been an issue in your plant. But if you see a lot, you start to know your bacterial population is getting too old and your plant might start to experience problems after it. So I just included this video for fun. This is a rotifer eating some bacteria. You can see it has its spinning heads here, vacuuming bacteria into it. We have a nice little spiral going on that it's producing. And over here you can see its mastox, which is like its jaw, which it uses to chomp down on bacteria. There's another one that happened to creep in on the top left while this video is being recorded. But rotifers are pretty interesting, so I thought I'd throw in the video. So there's some limitations to microanalysis. One we've talked with a couple of times, and that's that if you don't have information as to what the plant's microbiological population looks like during healthy operation, you can't necessarily say whether a filament or an organism is an indicator of a problem. You might have a plant that always has low F to M filaments, and they actually help it function and produce flock better. So if you lose these filaments, you might have an issue. And in fact, the population might actually look fairly abundant of these filaments. So in another plant, it might be causing a problem at the same levels. It might be bulking. So the lab you're working with doing the microanalysis, they'll tell you you have the filament. If you're having a bulking issue, they'll say this filament may be contributing to the problem, but they can't really know what thing causes the problem and what thing is normal for plant operation. And generally, you'll see a couple different types of filaments present at the same time. And if a couple of them are in similar abundance, it can be hard to point to which one is the real problem causer and which one might just be there consequently. So to use microanalysis to assist plant function, just remember to keep running it when your plant is functioning well occasionally, particularly at different times of year. It's usually good to run about 4 microanalysis tests per year at kind of a minimum, just to get a sense of what's working in your plant, even if everything is functioning well. And then, of course, if you have a problem or an operational change in the plant, it's nice to send a microanalysis sample because the bacteria are doing the work in the system, which means you're going to want to take a look at how they're doing and how the conditions are affecting them. So chemical analysis, I'm not going to talk quite as much about, but there's a couple things people typically look for. Influent analysis, some of the bigger plants run all the time, but some smaller plants use it primarily diagnostically when they're encountering a problem. You might look at incoming BOD, ammonia phosphate, that kind of thing, and you might be looking at the nutrient composition to see how it's contributing to issues experienced in your plant. You might look at specific zones in your plant to analyze the nutrient levels. So for example, you could have an aeration basin which has a sludge deposit in it at the base of the aeration basin, and you could have pockets of anaerobic activity in your typically well aerated basin. But this pocket of anaerobic sludge might be pumping excess ammonia back into your aeration basin, which might be contributing to increased ammonia leaving in your plant effluent. And you might be confused just if you were to just analyze the influent, because you might not have any changes in what your influent composition have been. There might not have been any environmental changes that have been occurring that have been substantial enough to do what you would expect, which is to impact the nitrifiers. So what you're seeing is decaying bacteria, and you won't really know it unless you won't know where it is, or if that's the case, unless you're analyzing the nutrients in different regions of the plant. So you test one of your aeration basins, you notice that one has elevated ammonia. There's a good chance that one would have sludge accumulation in it. Toxin analysis is maybe a little bit more hit or miss. It's nice to be able to send out analysis for toxins such as like quaternary ammonium cations, for example, we work with a lot. But the problem is you could have a toxin enter your system at any point of time, and if you look at the influent, it might not be present there when you're taking the measurement, or it might be present at very low levels, but at a different time of day, a large amount of it has been discharged to your plant. The other thing is you can't always tell whether the toxins are active or not active in your plant. For example, if you were to take a sludge sample from your aeration basin and measure quat levels in it, you might notice elevated levels of quat, but a lot of that quat might be stuck to dead and inactive bacteria anyway, so it might not be having any effect on your process at that point in time. So that one's a little more difficult, but it is a possibility in some cases, particularly if you're able to look at a specific time when one customer or client your plant is working with is discharging their waste. You can look to see if there's elevated levels of disinfectants. And you can coordinate upstream in cases where you have a good relation with the industry to know when they might be discharging cleaners, so you can get a sense for what levels are entering your plant. So the main things here with using chemical analysis, nutrient analysis is sort of the most valuable and commonly used one, where in aerobic systems, you can just look at your BOD to N to P coming in. Usually we'll look for BOD, total nitrogen, and total phosphorus. There's a couple different ways you can look at this. You could look at ammonia as the N, or you could look at total kilojoule nitrogen, which is organic nitrogen, as the N in the ratio. But usually people just go with total nitrogen and total phosphorus for simplicity's sake, and try to adjust the ratio of 110 to 1. Now, it could be a little lower or higher, and your plant might still be functioning great, depending on your bacterial population, depending on how much of each of these are active. But if you find you're way out of whack, then you have a pretty good sense of what the problem is being caused. Anaerobic systems are quite a bit different, but I did include a value there for reference. We already talked about toxin analysis quite a bit. And you can also look at things like sulfur levels, ammonia levels, that kind of thing to get a sense for issues. Like if you have really high sulfur, your plant might be more likely to experience problems related to sulfur reduction or hydrogen sulfide than some of these other problems. So it gives you a wide range of things you can keep an eye out for. All right, so just a couple other interesting things I'm going to mention, but not go into detail. We do have a lot of customers who run fatty acid analysis, which gives you kind of a breakdown of fat chains in your wastewater plant. You can look at how broken down the fatty acids are, how many of them are full fat structures versus decomposed, and it gives you a sense of how the decomposition of fat is working. We don't see that as often. It's more of a specialty test, but it can produce some interesting results. ATP analysis is one that would be nice if a lot of plants could run more frequently. It gives you a sense for what the actual active biomass in your plant can be. That would be its sort of main feature, but it also can give you a sense as to how much stress your system is experiencing. But active biomass I like to focus on because a lot of plants will look at their MLSS or MLVSS numbers and think that's all active bacteria, but in fact, 70% of it might be totally idle, inert junk that has no contribution, like dead bacterial cells or grit, just inorganic crystals or something like that. They all will occur and be measured in your MLSS and to some extent your MLVSS, but they're not actually active bacteria, which means they're not contributing. Another thing we've also seen more frequently recently is DNA sequencing. A number of companies have abilities to do some metagenomic analysis on wastewater plants to give you a sense for what level of nitrifiers you have, what level of phosphate accumulating organisms you have. They might be able to provide you a definitive identification on some filaments if you're noticing something in bulk. It's usually best to pair that kind of thing with microanalysis, but it produces a lot of interesting results in some cases. Okay, so the final thing is treatability studies. Treatability studies are a very more complex and intensive test where you're attempting to determine something like these three things. Like if a waste substrate can be degraded at all. As a plant, if you were receiving a new waste stream, you would want to do a treatability study to see that it is in fact able to be degraded by your process without causing any problems. So you might blend your new waste stream in with your typical waste stream at appropriate concentrations and see how it impacts something like in the background I have oxygen uptake test set up. You might look at oxygen uptake rates and see if your plant is still able to uptake oxygen at an appropriate rate, because the faster your bacteria are uptaking oxygen, the faster the metabolic activity is. So a fast oxygen uptake rate is a good indicator of metabolic function, and it's a good indicator of substrate degradability. You could be using treatability studies to try a bunch of different supplemental nutrients in your plant. If you're concerned about a nitrogen deficiency or if you have a phosphorus deficiency or that sort of thing, you could run some side-by-side reactors in this type of study and add a certain amount of different nutrients and kind of determine how much of a nutrient supplement, it could be a micronutrient too, might be helpful in improving a variable you're looking at. For example, BOD removal. Maybe if you add nitrogen, you'll be able to remove BOD more efficiently in your system. And you can also, in some more complex cases, determine how operational changes might impact a system before increasing the scale. So sometimes people do this with a pilot plant, and that is already a very large scale in itself. So it can be nice to have some sense in a smaller scale, like a lab scale, kind of a 500 milliliter reactor. If you can measure things like different levels of DO, how they impact plant operation, how different wasting amounts might impact plant operation, that sort of thing tends to require a more complex setup than the previously mentioned two, but it can be valuable if you're planning on making changes to your system mechanically or procedurally. So I just have an example graph here of oxygen uptake, because I like that type of testing and it's usually a very good indicator. So this was an oxygen uptake rate test with supplemented quaternary ammonium cation, which is a toxin. And you can see the higher dose of quats produced a lower oxygen uptake rate. Here we have our 5 ppm quat dose. Here we have a 3 ppm quat dose. Here we have a 1 ppm quat dose. And all of them were distinguishable and worse than the control. So you can see very clearly how the addition of that amount of biocide in this case was influencing the uptake rates of nutrients by bacteria, and it can give you a sense of how much the quat is actually hindering your system and as if that's going to make a difference to your plant operation. So I do want to quickly go over sampling requirements. I know that was talked about a bit earlier, but remember, different tests require different forms of preservation and different types of samples. And you're going to want to be very careful to make sure you understand all the sampling requirements completely before you collect the samples, because it can actually be destructive if you're sending a sample that is not representative of your plant. You might get recommendations which are directly contradictory to what you're supposed to be doing. Yeah, if that happens, there's no way the lab is going to know. They're just going to have to assume you collected the samples correctly. So this kind of comes down to a lot of communication things with the plant to make sure they tell you clearly what's going on. So just a couple other notes. Diagnostic testing, if it's not too expensive to run regularly, it's beneficial to run it more often. You might want to run, if you can afford microanalysis with an outside plant monthly for a full year, you might want to go ahead and do it because you'll be able to better understand your bacterial population over a period of time, how it changes throughout the year, what sort of operational changes might influence it, and get a better sense for how to maintain a healthy population. Microanalysis, yeah, and microscopic observation can take a while to understand. So sometimes when you're looking at stuff on site, you might have a good sense for what's occurring at the specific time, and you might be able to look at what filament levels and flock structure are typically like, but the lab you send your sample to, if you were to send a sample out, um, may not have an understanding of your baseline. So make sure to have a baseline sample. And many labs are available to consult on what type of testing you should run to address a problem. So if you find yourself in a situation where you're totally confused, it's always acceptable to look for outside help. You could go through any consultant or different lab and they'll kind of help to point you in the right direction. All right, so just a couple things. Here's a quick summary. Make sure to have a baseline for diagnostic tests to determine how your plant is diverging from healthy function. Have specific goals. Verify you 100% understanding sampling requirements and hold times. Make sure the lab you're working with understands what's going on. You may want to verify that that lab is in fact legitimate. I actually like it if people get references from different customers using a lab. It's nice to have at least somebody who says, yes, we had a good experience working, because sometimes you'll have difficulty communicating. Your results might be turnaround slow. You might not be sure if your results are good. Sending it to a lab that's not as legitimate as it should be. Most labs are pretty good, but you always want to be kind of on the lookout for that. And make sure to remember, previous diagnostic analysis gives you insight into future problems. So always be ready to look at the past analysis you've had done to inform your future decisions. So I just want to say thank you to all the people working in wastewater operation to help protect environmental health. It's an invaluable service. Everybody is benefiting from wastewater operation. And if you have any questions, please contact Dan McKeaton at team, which I have my email right there, dan.s@teamaquafix.com if you want any consultations for lab analysis. Thank you.